Hello there. We've been talking about the eigenvalue problem and free vibration, and we've solved some problems on free vibration analysis also. Today, what I will talk about is something to do with practical free vibration analysis. Now, this is a large class of problems. Last time I actually introduced you to the concept when we looked at that. Look, after all, we saw that this was the problem that you solved. Okay, so this is the free vibration problem, and this is the eigenvalue problem. And then we saw that, look, essentially what the determinant of k minus omega squared m was equal to 0 gave was that there was, where if you put omega squared equal to lambda, then we got basically a function, and it's a nth order polynomial. And one of the ways of practically finding out frequencies is from doing essentially root finding algorithms, right? And root finding algorithms, there are many. So, you basically have to find out the roots of this function, and from that you get lambda 1, lambda 2, lambda 3, and then there are tests to show how you don't miss any root. Okay. Now, this is this is something that is done typically in a numerical methods course. So, I am not going to talk, excepting for the fact that this writing down the polynomial and finding out the roots of the polynomial is one procedure for doing practical free vibration analysis. Okay. Now, today I am going to talk about another method, and this actually, before the advent of computers, this was the best way of finding out the frequencies of a system. Okay. Before advanced computers, I mean, you still had to do matrix analysis, but matrix is much easier to do in a computer even way back in those days. Okay. And this method is either called the inverse iteration method, or it is called the, to give its old name, the Stodola method. Where did this method start? The method started from the fact that if you looked at that, you have a situation where the problem becomes k phi is equal to omega squared m phi. Okay. So, now if I were to rewrite this, I could rewrite in this format: 1 omega upon omega squared phi is equal to k inverse into m into phi. Okay. And k inverse K inverse is actually the flexibility matrix. Okay. So, it is not as if you are doing K inverse, you can actually find out the flexibility matrix directly. You do not have to do K inverse. Okay. So, you are essentially doing something like So, call this matrix a D matrix. So, then this problem can be written in this format. This is the basic concept behind this problem. Okay? So, now D matrix is a property matrix, you can derive it. Okay? So, D is known. Okay? Now, this is equal to this if this displacement that you get is actually, sorry, let me put it this way, that right. So, this is phi n, omega n, phi n into phi n. So, this is omega n, phi n, d phi n. Now, this is true if this displacement, or this is a displacement. After all, phi is nothing but the displacements corresponding. Only thing here is that it is a shape. So, that is okay, that does not matter, it can take any displacement. Okay? Now, this is true. However, the Stodola method says is that, look, you start with a specific vector. Okay? So, you start with a vector and we will call this vector V1, okay, and you start with a vector, that is the 0th. Okay? So, this is a n by 1 vector, it is a column vector, right. Okay. So, take any vector, you think up a vector and think of it. Okay. So, then what we say is that, look, by definition, and you assume this to be the fundamental, kind of an approximation of the fundamental mode shape, then we can say that, look, it is equal to this 1 is equal to d into V1 0. Okay. Now, what you do is, okay, you do not actually do this. So, what you do is the this is this procedure. Now, you do not know what omega 1 is, right? You do not know what omega 1. So, you call this as okay. And now, the trick is to compare okay. So, now what you do is you normalize okay, this V1, you normalize, because every time you multiply with D, you need to bring it back. So, let us say you start with something like blah 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 1. Okay. So, after multiplying by D, you get some value. Now, this is a shape, this is not a displacement. So, what you do is you normalize this and bring it back into this format. Okay. So, you are essentially bringing it, then you are comparing V1 and so the way you go from this to this is through a standard normalization. Okay? So, compare. If they are not same, then you do this, you do and then standardize it again to get V2. Compare. So, this is an iterative procedure. Okay? And since this is an inverse iteration procedure, you will get to a situation where, let us say, R, some rth iteration, and this is equal to R minus 1, right? And from that you find out V r. Now, let us say that V r is equal to V r 1. Convergence. Okay. So, now the trick becomes that, look, if you look at it, since this is equal to this, we know by definition that, look, is equal to 1 upon omega 1 squared. It is actually 1 upon omega 1 squared V, but we do not want to find this out. So, what we do is we do this. Okay? And how can you find out omega 1? Well, you can take any k, and if the two of them are equal, you will see that any k, okay, k it's omega 1 squared is going to be equal to V k r minus 1 upon V r. Okay. So, that is my omega 1, and this omega 1 is actually the fundamental frequency. Now, you may well ask, how did that happen? Well, again, the convergence of this procedure, okay, to the first mode, the proof of the convergence actually lies in a very fundamental aspect, and that is that you can write it in this format. Okay, I will prove it to you in a rather simple manner. Actually, why should we? Because it is not really very relevant for us to solve it, and because again this is a numerical method, it can be shown that this converges, and it converges to the first frequency. You can look up any of the books that I have given you as reference for solution to this particular procedure. Okay. So, now the trick is to, so we can find out the first frequency. Once we find out the first frequency, please note that to get the first mode shape, you still go back. There is no other procedure than simultaneous equation solver to get phi 1. Okay? There is no question about that. So, now the question then becomes, so you can this is not an issue at all. Okay? So, we found out omega 1 and phi 1 using the inverse iteration or the Stodola method. I hope you understood what the method is. Okay. After I am done, we will actually try to solve some problems with this, and I will show you what I will do is I will solve the problem that I have done last time, and we will try to see whether we can get to the equation. Okay. So, now the question then becomes is that okay, and whatever V1 you start from and you do the inverse iteration, you use the iterative procedure, you will always converge to this. It does not matter, it can be shown. It is just that if you use bad initial vectors, this is the initial vector, and this vector is chosen any arbitrary fashion. For example, a classical initial vector is just a vector of 1s. Okay? It does not matter what your initial vector is, you will always converge to get omega 1 and phi 1. And note that, by the way, the phi 1 is essentially the V 1 R is really the phi 1, okay, because it satisfies this. Okay. So, in other words, whatever you start from, you will always land up here. So, how do I use the inverse iteration procedure to get the higher modes? For example, let us say I want to find out the second mode. How do I find this out? Now this becomes the crux of where I have to go back and look at a specific form, and that is, note that any displacement vector V is what? It is actually, if you look at it, this vector would be V 1, V 2, V n, isn't it? So, now this is equal to, I can say, is equal to V 1 plus V 2 plus V n Do you agree to this? This can be written in this form. I mean, after all, it is nothing but V 1 plus V 2 plus, and that is what this is. Okay. So, in a way, we can say that this is equal to a kind of this is the unit vector, right? This is a unit vector. Okay. So, blah blah blah, and this can be then obviously written as summation I going from 1 to n V I into, where this is the unit vector where the ith one is 1 and everything else is 0. That is what this is. This is a unit vector. Okay. So, we can write it. So, in other words, any n by 1, and what are these? These are like the amplitudes. This is like an axis, isn't it? These represent axis. So, in n dimensional space, what do these represent? These represent axes. Think about it. In 2 dimensional space, what do the axes represent? Right? 0, 0, 1. So, x is 0 and this is 1 is one axis, and 1, 0, because y is 0 represents the other axis. So, in other words, these represent the axes, all these represent axes, and these represent. So, if you have like let us say V1, V2 space, I represent this. This is represented by V1, V2, okay, which is nothing but V1 into the unit vector along 1 plus V2 into the unit vector along V2. So, that is what this is. So, these represent, if you look at these represent amplitudes along this axis. So, in a way any displacement is a representation of a point in n dimensional space. Okay? So, that is what it is. A n degree of freedom displacement is essentially a representation V, a representation of a point in n dimensional space, where we know that these represent orthogonal sets. These are orthogonal. This one does not contain this one, does not contain this one. So, none of them contain each other. They are orthogonal. So, that is why we say n dimensional space, because each value is the amplitude along an orthogonal axis. Do you agree to this? I have already shown it. Specifically, if I show V1, V2 and I should look at this point represents a displacement pattern. Okay? So, of course, n dimensional space I cannot show it to you, but I can at least tell you that look, this is how it looks. Okay? So, therefore, that is very important. Now, if you look at it, any orthogonal, so this point, this V can actually be represented in any orthogonal axis space, as long as it is n orthogonal axis space. Okay? So, now let us look at one space, one such space that I know. One such space that I know is, and we know that phi 1 and phi 2, okay, I mean I am talking about phi I is orthogonal to phi j. I know that because they satisfy the orthogonality condition. Okay. So, therefore, I can represent the displacement just like I represent it, I can represent it in this fashion. I going from 1 to n phi I into, now I will call this, what does the phi I represent? Well, it represents a direction in the n dimensional space, which is orthogonal with respect to every other space. And what is this? So, this is the mode shape and this is modal amplitude. And note that this mode shape is a n by 1, and I know that this one does not contain any of the other modes because they satisfy the orthogonality condition. So, what I have done is, if you look at it, what does this line represent? Let us say 1 1 line, and this represents the 1 minus 1 line. Okay? So, now if you look at it, remember the problem that we solved earlier? Did you remember that we got V 1 and V 2? We got 1 1 and 1 minus 1. Remember that? Okay. When we solved it in V x and V y, we got 1 0 0 1. So, that was almost like saying that unit vector along the x direction and along 1, which was u x, and 1 0 was along u x, and 0 1 was along u theta. Now, when we defined that by V 1 and V 2, we got phi 1 as 1 1 and phi 2 as 1 minus 1. So, you see, this is the original space for representing V 1 and V 2, which are basically V x and V theta, and I can also represent them in this axis, which is 1 1 1 minus 1. They are orthogonal with respect to each other, and this point then will have what? It will have this as my y 1 and this as my y 2. So, you see, those are the amplitudes. So, those are the modal amplitudes. Okay. Now, the advantage of this is the following, that if I were to do the following, if I were to pre-multiply both by, let us say, phi n transpose m v, then I pre-multiply the right hand side also with phi n transpose m integration from 0 to I phi I y I, right. Now, if you put this in, is equal to summation I going from 1 to n phi n transpose m phi I into y I. This we know that if I is not equal to n, this is equal to 0. Okay? This is equal to 0. So, therefore, what does this become? This then becomes the following: only the term phi n transpose m phi n and y n. Okay? So, now, so what is the modal amplitude equal to? It is equal to phi n transpose m v upon phi n transpose m phi n. Okay. This is the modal. I can, if I give any displacement quantity, okay, I can always find out the y n through this procedure. Okay. I can always find it out. And now the trick becomes that, well, let me now say that, look, let me start with a displacement quantity V 2 0. Okay? And now what I am going to do is I am going to find out, okay, I am going to do what? I am going to do the following. I am going to ensure that this is equal to summation I going from 1 to n phi I y I. Okay? So, therefore, I can always find out y 1. How can I find out y 1? By just doing phi phi 1 transpose m V2 0 and differentiate it with phi 1 transpose m into phi 1 transpose. Okay, so I can find out. Now note that I am trying to find out the second mode. I can only find out the second mode if I have already found out the first mode, omega 1 and phi 1. I already know those. Is that clear? I already know that. And what is phi 1? Phi 1 is actually the V1 S. Okay, this is equal to this. So I have to use the inverse iteration to first find out the first mode. Now once I know this and I take any mode, I can find out y1. And what I do is I find out a new V0 which is V2 0 minus phi 1 y1 0. If I subtract out this, now I know this, okay, I have found this out. From this, where I know this, and this. So I can find this out. Once I find this out, I know this and this. I know this because that's what I started with. Okay, I can get a new value. Okay, a new value. This one does not contain any first mode contribution. So in other words, what we've done is we've swept away the fundamental mode. We've swept it away. Okay? If we've swept it away, okay, then what we do is the following. So now what happens over here is that you get, now note that if you look at this particular one, okay, let me rewrite this in a specific way. So what we are doing is you have phi 1 y1 0. This is equal to phi 1 into phi 1 transpose into m. Okay. So now what are the units? Well, let's look at this. This is an n by 1, okay, into V2 0. Well, 1 upon, we'll call this m1, where m1 is equal to phi 1 transpose m phi 1. Okay, we've already gone through that. That's a scalar. Okay, so this is a scalar. This is n by 1. This is 1 by n. This is n by n. So if you look at this multiplication, this is nothing but an n by n. Okay, so this n by n matrix normalized with this, I'll call this as my S. Okay, so this is S into V2 0, where S is an n by 1, this is an n by 1. Okay, so phi 1 0 is this. So if you look at this, V2 0 tilde is nothing but V2, okay, 0 minus S1. This is S1 because it sweeps out the 1. Okay. S1 into V2 0. So, this I can call as I minus S1 into V2 0. Note that since this is n by n, I have to get a equivalent this thing. Okay. So, now if you look at this, okay, sorry, I will call this as S, right. This I will call by S1 tilde, and this I minus S1. So, what you are doing is you are taking I is nothing but the identity matrix, which is nothing but 1, 1, 1 only in the diagonals. Okay. So, this into S1, this I will call S1 tilde I will call as my S1 matrix. So, now if the first thing, and this S1 matrix is a known matrix, known. Okay. So, the first thing that I do, that is I choose any vector V2 0. The first thing I do is sweep this sweeps out first mode. Okay. Then if we can write this in this format, that find out V2 1 hat is equal to d into V2 hat. Okay. Now, next check V2 1, this is normalize, and check against V2 0. Then iterate that this becomes now V2 2 is equal. Now the thing is that as soon as you find out V2, check this first. If it doesn't work, then what you have to do is take V2 1 tilde is equal to S1 V2 1. Plug that in here. Okay. Get the next one. Sorry, 1. Okay. Find this, continue doing this. Every time you get a new vector V2R, you should sweep it to get the V2R. Sweep. All the time you should sweep it. Every time sweep it before you put it back into the iteration. If you sweep out the first mode, then the swept, this one, does not include first mode, converges to second mode. Ultimately, this one, and the only thing is you have to sweep it in every iteration. Why? Because if you don't sweep it, some value of what will happen is, if you don't sweep it, some value of the phi 1 will come into this one, and if you iterate it more, it will converge to the first mode. So, you have to sweep out the first mode at every instance, every iteration. The first thing is check this. If this check is not, then take this, put it into this, sweep it out. Take this, put it in here, find out with D, find out the next one. Okay, normalize, check. If it doesn't, go back, sweep. Sweep. Everyone has to be swept. Everyone has to be swept. If you don't sweep it out, then you are always going to converge to the first mode. Okay, so you have to sweep out the first mode. If you sweep out the first mode, every displacement quantity that you get does not contain the first mode, it will converge to the second mode. So this way you can find out omega 2 and your V2, which is effectively phi2. Okay? So this one, this is how you find out the second mode. Well, this procedure you can continue using because you can always find out that you need to just sweep out. Now you understand how to get higher modes? Well, you want the third mode, what do? Well, if you want to find out the third mode is equal to this minus y1 into phi1 minus y2 into phi2. These we have already discovered how to get these. The way to get them is, well, y1 is equal to phi1 transpose m v3 0 upon phi1 transpose m phi1, and y2 is equal to phi2 transpose m v3 0 phi2 transpose m phi2. This is the way you can find out these two. Once you find these, you can get them out. And again, we can write down the sweeping matrix, okay, for the S1, S2 sweeping, okay, S1 to sweeping, it will become I minus S1 minus S2 tilde, okay, where S1 tilde is nothing but phi1 transpose blah 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 blah, okay, and S2 is going to be equal to phi2 transpose into this, okay. So this is, and then you just every time you get a value, you sweep it and you get the clean value. Once you get the clean value, it will not contain the first mode and the second mode, and if it doesn't contain the first mode and second mode, it will converge to the third mode. Okay. So this in a sense is what we need to do where you are looking at this thing. Now how do we converge? Now how do we get the highest mode? Now we can't keep doing this. So if you have 1000 degrees of freedom, you can't keep getting every one of them and then going ahead and doing it. So the way you do it is that you generally just look at this particular solution. That if you go back there, k minus omega squared m into phi is equal to 0. So what you do is k phi is equal to omega k phi n is equal to omega n squared m phi n, right. This is, this is only valid for a specific omega. Is that clear? But that's why you can't just write it arbitrarily. Okay. So it's valid only, it's equal only in a particular ohm. And what I'd like to do is I'd like to pre-multiply both by m inverse k phi n is equal to omega n squared phi n. This is known as, again, the Stodola method. The only thing that happens is that this now becomes your d, and the way this goes is you define a Vn 0 and then you multiply it by this. I will call this E because this is different from that. So, multiply it by E, which is m inverse k, okay? And typically m inverse, what do we do? M inverse, okay, typically if we use the lumped mass, m inverse is just the, the 1 upon m at every diagonal step. Okay, so m inverse is actually very simple to get, okay, and that if you multiply with k, okay, that one becomes E. So, what you do is you find out by E, okay, and then of course, you go Vn 1 compare with Vn 0. If it does not work, go back, okay, and find out Vn 1 E Vn 2 tilde, and ultimately the thing that happens is that V n r is equal to omega n squared into V r, okay, minus 1 V n. And so, what we have is omega n squared basically becomes any V k of n r tilde upon V k n r minus 1. This is my omega n, okay, and this is how this entire thing. It can actually be shown that if you use this direct iteration, the direct iteration actually, this is not the inverse iteration, this is the direct iteration. If you take the direct iteration, you actually converge to the Stodola method. Okay, I mean you converge to the highest frequency. So, this one turns out to be the highest. Sometimes finding out the highest frequency is required because it gives you an idea of lots of things. I mean, basically because sometimes what happens is, considering on the lowest frequencies, if you are looking at, for example, frequency domain analysis, you do not need to consider a kind of a large enough range of frequencies. Okay, we can remember that it is discrete Fourier transform. Remember the Nyquist frequency? Okay, well, the Nyquist frequency should always be greater than omega n. Okay, and that is the reason why we always try to find out this. Okay, now that here is that this is an I have taught you in two ways. One is root finding and one is iterative. Okay, the inverse iteration procedure. Now there are lots of other procedures. There are, I mean, I will just write them down. I am not going to discuss them here. For example, subspace iteration. Okay, this is actually in a way, this is here you are doing frequency by frequency. Each one, the subspace iteration is where you take a space. So, instead of having a specific, you sweep out certain ones, and so that you can get a block of frequencies in one shot. I am not going to go into this. If you are all interested in it, you can always look up other methods. Now, in certain kind of structures, especially for example, structures that are not stable. For example, for a frame building, okay, you do not get zero frequencies. But suppose you have a satellite. Okay, satellite is also a structure, and you would like to investigate what kind of dynamic behavior happens up the top. Now, you have what is known as zero frequencies. In other words, what is a zero frequency? A zero frequency is where there is only rigid body movement. If there is only rigid body movement, there is no deformation, there is no strain energy. If there is no strain energy, k is 0. Okay? If k is 0, okay, m is non-zero, so obviously omega is 0. Okay? Omega, so 0 frequencies. Okay? So any rigid body mode has 0 frequencies. In that particular case, how do you eliminate 0 frequencies? By looking at what is known as shifted subspace iteration. You know, we really look at 0, lambda, we know that these lie in this domain. But suppose it lies in this domain, all that you do is take a delta shift, put it here, put the axis at a known delta shift away, and now this becomes a specific one. Okay? So, you can do that, that is called a shifted subspace iteration. Then there is the Lanczos method. These are all methods that are used for practical vibration analysis. So, root finding, inverse iterations to roller method, okay, subspace iteration, shifted subspace iteration, Lanczos, these are all various ways of doing practical free vibration analysis for real structures. Okay. So, I will stop here. Thank you very much.